Good morning. How are you?
Good. How are you?
Okay, so I'm JP Vasseur, I'm a Cisco Fellow, and pretty excited to talk to you about what I think is going to be very important for the next few years, and what machine learning can do in artificial intelligence in general for the network. As a quick intro, I've been at Cisco for 19 years. Started working on the internet for QoS, MPLS, fast reroute, opticals, and then I moved to the IoT for about 5 years. Then I run a project related to security and machine learning for 3 years that we shipped last year, and I've been now driving a new project related to machine learning for the network in the cloud. So this topic is not related to a particular product, but more of a technology. So interrupt me anytime you want, especially if you have opinions about that. Usually people are very opinionated about machine learning in general. So this way we can make it entertaining. So let me start real quick with where I think we stand. AI was born almost 40 years ago with the perceptron model, which was a fairly basic classifier. And we haven't seen so many progress for quite some time until really the last decade. When you look at where I think we stand now, there are a lot of things interesting happening, self-driving cars, and there's a lot of technology in there related to machine learning. Lip reading, by the way, we know now that the machine can outperform human in doing the lip reading, counting people, machine talking, and things like that. In the area of gaming, by the way, it's pretty interesting to note that Deep Blue with a chess game was interesting, but not so revolutionary at that time because it was a brute force approach. When you look at the game of Go, where you've got so many combinations that you cannot have a brute force approach, we started to use machine playing against each other and improving over time. And that was a pretty interesting step forward. So let's look at how we can use these technologies in the context of networking. So I brought up that slide because that's usually the first question that I've got. What kind of machine learning algorithm you're using? And interestingly enough, and we've been working on that for almost 7 years now, this is not the most relevant question. First of all, we are using a set of algorithms. There's no one size fits all. There's a lot of buzz around deep learning these days, and this is super promising, but it's, you cannot unfortunately use one algorithm to do many things. So what is relevant though, and I just wanted to share with you some lessons that we learned over the years, is one, to work on a clean data set. And we know that in our world of networking, there are usually a lot of signals and things like that. And for the machine, when it's getting too noisy, it's extremely hard actually to interpret. The second one is to really understand the network so that you can tune and architect the algorithm in the right fashion. If you provide too many signals to a machine, it's very unlikely that you're going to get any interesting results. And what we've been doing in my team for many years now is actually to combine the expertise in machine learning with networking, find out what are the right signals that we're going to be using. I'll give you some really cool examples about that. The second one is about false positive. So that one is also very interesting because in the area of security, for example, if you tend to raise too many false alarms, very quickly the user will not take that into account. So your worst enemy is a false positive. In other areas, it might be the false negative, and there's always a tension between the two, because if you make the system too sensitive, you will indeed detect pretty much everything, but with a lot of noise and lack of accuracy, making the system pretty much irrelevant. Robustness across data set, that one is particularly interesting. When you train a machine to do a specific task, and you train it using one data set, there might be an issue which relates to what we call overfitting. In other words, the system will will get too close to a specific data set, and when you use the same algorithm in a different data set, you lose some generality, if you will, and you cannot really apply it to different data sets. So there are many algorithms to do that, but this is one of the rationale for being in the cloud, which is that we're going to see a lot of data from very diverse networks, so which makes it very powerful. That one is really interesting as well. It's about interpretability. With some algorithm, they can provide an output, but they can't tell you how they reach that state, if you will. And I could share with you many anecdotes, but one of them is at some point we developed an algorithm that was trying to model the behavior of a host in the context of security. And the algorithm was really, really strong at detecting anomalies, but when raising an anomaly, it couldn't tell you what was wrong. So there was no way to interpret the result, making the system not very usable. And scale, is obviously there. So here is where I think we stand. There are usually two camps. The pro machine learning who think that everything is about machine learning and that's the future. Another camp who think that there's nothing good about machine learning. The truth is, of course, in the middle. And I absolutely don't believe that we should be using machine learning for everything. There are many of our approaches that are much better depending on what we're trying to do. But we know that machine can learn. And I try to give you a few examples on how we can use that before the network. All right, so here is how it started. At that time, I was in the IoT. And you guys are highly respected technologies, so you know how difficult these environments are. And the video that you see on the screen, by the way, is a real video. It was a 2 million node network running IPv6 for smart grid. And we had to face a number of issues, like the lack of stability of the links, the constraints on the node, no memory, no CPU. So we came up with a lot of different technologies, new QoS for low power and lossy networks, 15.4, for example, new routing protocols and things like that. So the question that we had from a few of our customers is, can you predict the delay in this network? Which was extremely hard to do because we could not push the data, the raw data in the cloud, first of all, because there was a lack of bandwidth. And second, there was no mathematical algorithm capable of bounding the delay and doing some predictability. So that's where we started to look at machine learning AI and how we can use these technologies at the edge of a network. So this is really how it started almost 7 years ago. So now what I like to do, oh, by the way, do you have any comment, any opinion about machine learning in general? No? You do?
Mine's just blunt right now.
Okay.
I mean,
Soaking it in.
just a comment. We have to get there. I think we see the explosion of all these devices. IT's being asked to do more with less, right?
Right.
It's the only way that you're going to be able to get the kind of visibility that you need.
Right. Totally, I agree with you. And one of our top executives asked me the question after the second project on machine learning. He said, what is the main outcome? And what I told him was, I think that we have learned where not to use machine learning, because if you rush out, regardless of the type of problems, machine learning is pretty complicated. So we need to know what it can do, what it cannot do. But I agree with you, the massive amount of data makes it really relevant for many problems. So let me give you a few examples. The first one was a product that we shipped last year. The name, I think, is StealthWatch Learning Networks now, and it used to be called Self-Learning Networks. I drove this project for 3 years. It was about using machine learning to detect zero-day attacks in the network. So the basic idea was, we know that how firewalls, IPS, IDS technology work, and they are very efficient, but they are based on signatures. So what do you do when you have zero-day attack? By definition, there's no label, there's no signatures. So we thought, well, if we can start trying to do the opposite and model what is the normal baseline, if you will, and find out some anomalies, that could be a very interesting approach to take. So here's the architecture at a high level. So each node is effectively, so on this router that you see here, it could be a router or a switch, by the way. The machine learning algorithm is running on premise, on the box. And what it does is first of all, we have access to a lot of data because we have NetFlow that we can consume locally. We can do deep packet inspection on DNS requests, for example. We have the logs, and we have access to a ton of data without exporting anything. So now the way the machine works is we look at hundreds of dimensions. Could be the time of the day in order to detect new flows that we've never seen before, the destination, for DNS requests, name of servers, and many, many things like that. And we looked at all these dimensions. We built a mathematical model online, and we tried to make it robust enough so that when we see something quite unusual, that could be because of a zero-day attack or data exfiltration, for example, we can detect it immediately on the router. So if you got a network with thousands of routers, you effectively have thousands of models running in parallel. And each of them would basically send an anomaly to the data center, where we aggregate all of the anomalies being raised. So what we found out, of course, is that, and by the way, I forgot to say that upon receiving the anomalies, we then have access to ICE so that we can bring more context. We have thread grid and OpenDNS and many other tools so that we can add many more context to it. Of course, the interesting aspect about this one is you need to use anomaly detection, and the issue with anomaly detection is potentially false positive. And if you raise too many false positive, at the end, the user will not listen at all, and it becomes very inefficient. So we took a very different approach here. We tried to use what we call reinforcement learning. And so the way it works is very simple. You raise the anomaly, you give all of the context, and the user would just give a thumbs up, thumbs down, without having to indicate what was the reason why it was a good anomaly, it was a bad anomaly. And then, consequently, what the system is going to do is to learn from its own mistake and don't do it again. So just to give an example, if you keep saying that you don't want to see an anomaly related to new flows for specific protocols, the system will learn that these are the common traits. Each time you give a thumbs up, it is because of a number of things, and then we filter out programmatically the false positive. And it doesn't take a long time. This is really the thing, because if you need to have 1 million thumbs up, thumbs down, that's not going to work very well. But after a few dozens of feedback, you see that the machine will automatically adapt and learn from its own mistake.
Is that on a per user basis?
That's a great point. So we do two things in this case. So because this is on-premise, so in that case, it's on a per customer basis. And for each users, we want also to have different approaches, because some users may have different views than other users. So what we found out, for example, we looked at, we compared the results across multiple users, and you see a lot of discrepancy. Some users think that this kind of anomaly is great, and for another one, it's not great. So the system does that on a per user basis. And we are looking also at ways to disqualify, when one user keeps saying no or yes all the time, and it becomes, we see a lot of discrepancy between one user and the rest of the community, the other users as well.
Just to clarify that, we should talk about, make sure users versus like an organization. You're talking about more of the organizational level, it sounds like.
Yeah, so basically in that case, again, this is on-prem. So the learning manager that you see, you have one learning manager per enterprise, and you have multiple users in the enterprise, which is in contrast with the second use case that I'll show now. Okay, so let's have a look at that new project. We'll be communicating more in the next coming month about this initiative. So here it's not related to security at all. This is really for the network in general. And this is a cloud-based learning architecture. So let me show you a few use cases that I think are pretty cool. So we are doing two things here. One is cognitive analytics, and the second one is predictive analytics. So let's start with cognitive. So the way I looked at that was, last year, so 2016, we looked at the experience we had acquired within Cisco about machine learning in the network, and we thought, what would be the really nice use case where we can apply these technologies? And with the increasing complexity of a network, we thought, we can certainly, especially with the cloud-based approach. Why the cloud? Because this way you have access to a ton of data, and you can train your models, and they become much richer and interesting. So one aspect is, if you look at, and I could give you dozens of examples, but I'll take just the example of throughput. With a rule-based approach, where do you put the threshold so that you can say, okay, the throughput given to Netflix is good or bad? Nobody knows what is a good throughput for a given application. So we thought we can certainly make use of machine learning to learn what was expected in terms of throughput. So in that particular case, the data is being provided to the machine. The machine will start doing some anomaly detection, and so that we can find out some issues. So in that particular case, here it's hard to read, but these are access points on the y-axis, and here you've got the device type. And so we said to the machine, find out issues in this network for the Netflix application. What you can see here is that the Netflix application is actually suffering, regardless of the type of device, for a few access points. Conversely, you see that a few access points over there only provide a bad Netflix experience to Microsoft Workstation in this case. And of course, we do that for all of the applications, and you see that the heat maps are all different, which makes it very interesting. We looked as well at a given app across multiple data sets, and you see that they all vary as well, showing back to your point that the amount of data is so big that only a machine can slice and dice in all directions. Now, where it becomes really powerful is when the machine can find the anomaly, then do some root cause, doing slice and dice in multiple directions, and say, we actually see that there's an issue with a given app in a given location at a given time, and it is only related to this release on the controller, this type of client, and at a given time, for example. And then you can root cause it, and that's going to be much more simple. I could give you many other examples, but that's one of them. The second one, which to me is even more interesting for the future, is can we start forecasting issues that will happen in the future? And I mean, I'm with you, to be frank. When we started to look at that, it was a little bit like we're thinking, well, is that even doable? So when the issue is random, there's no way we can forecast anything, obviously. But in many cases, we see that you've got some early signs that something is going to happen in a few hours. And this is where machine learning can help, because you show a massive amount of data to the machine, and the machine will start learning some early signs that are not detectable by a human and can start predicting what will happen in the future. I could give you a few examples, but as of today, if I take, let's see, roaming failure rates in a wireless network, several hours in advance with very high accuracy, we can predict there will be a catastrophic event. And of course, once you can predict and you can root cause, looking at correlation between all parameters, you can start thinking of fixing the issue even before it happens. So that's a very promising area there. So we talked a bit about wireless networks. Again, mobility patterns is another very interesting one, where we had a machine learning algorithm looking at all of the paths within a network and find out roaming failures and criticality, centrality of a nodes, and all those things. So we can use this kind of algorithm in many places. We talked about application behaviors. Network resiliency is, of course, extremely interesting. Can we find some interesting patterns with regards to noise, high error rate, link flaps, router reboot, AP reboot, crashes, and things like that. And of course, we've been working quite a bit on the WAN as well. Can we basically model the behavior of the internet, the public internet for SaaS providers? Can we potentially do proactive routing and start offloading, some links, knowing what the SLA should be, and all those things. So we are heavily working on these use cases as well. We'll talk a little bit more about the closed loop control in a few minutes.
I noticed on that last slide, I didn't see anything security related up there. And I know if you look at what Talos is doing, they claim to be using predictive analytics. Is that machine learning, or is that a separate group that's doing the Talos predictive analytics?
So they are also using machine learning. In that case, when I'm talking about closed loop control and predictive, I'm trying to, and actually the term predictive is a little bit confusing. We should probably say forecasting of issues in the future. And I'm more referring to the ability to say, well, looking at these signals, low-end signals, we see that an issue is going to happen in a few hours, and then we can now fix it, if you will, before it happens.
Gotcha.
Okay, so just a few things here for you. An example of cognitive analytics. We talked a little bit about the application throughput. The key takeaway here, which I think is interesting, is that when you look at throughput in a wireless network, an issue might be, of course, on the RF side, but it might be the link as well. Obviously, we all know that. So what makes this approach very interesting and very compelling is that we give visibility end-to-end to the algorithm. So we looked at the type of client. We can do dynamic profiling using ICE, for example, or on the controller. We have the inbound signaling. We get a lot of data about the type of device. We, of course, look at the wireless controller, the AP. We look at the WAN as well. So once you give all these control points to the machine will start building a model using a lot of input control point. Here, it's this graph here that you see, which looks very much like an histogram. It's not exactly an histogram. This is the model that has been built by the machine. So to give you an example, if you see X clients connected, trying to do different applications, what the machine will do in this case is to see what is the expected throughput that we should see in this array of network for this time of the day, for this type of client. And based on that, if we see that there's a big discrepancy, this is where we start detecting some issues. I could have given, other example like a roaming failure rate. We did a lot of analysis on many data sets. It's very interesting to see that you would expect the rate of roaming failures to be fairly low. It turns out to be fairly high, and not just because of a network. Sometimes this is the client. So I remember one data set. I think we had about 45% of failures because of a client, 45 because of 12 because of a network, and the rest were pretty much unknown. So we looked at that, and then we said, okay, what do we need to look at to first identify the anomaly and then the root cause? And in that case, you want to look at the client, obviously, the behavior of a client, but also the network, and finally the DHCP. DHCP timeout, for example, was a good example of root cause for failure when you roam. And this is, of course, giving the visibility of the algorithm is extremely powerful. And that's what we do with DNA, if you will. Question
on this. Is there a target? So one of the things with the cognitive analytics, it takes time to build up the data set and run it, right? Is there a defined sort of time that you guys are targeting to say, like, 8 hours is actionable, 24 hours is actionable? What is the, is there a goal?
Yeah, that's a great question. So in that case, with some of these systems, as you pointed out, what they do is they do one-shot learning, if you will. And so then in this case, depending on the objective, but some algorithm may take a week or 2 weeks before they have enough data. But in this case, because we're on the cloud, what we do is that we gather the data, whether it's SNMP, JSON files, you name it. We anonymize the data, it goes in the cloud, and this is an ongoing learning process. Okay. So it never stops.
So this is going to be, you said anonymous, so it's going to be aggregate across all Cisco customers kind of thing?
Okay. Absolutely. Okay. That's exactly the point. And it's amazing to see the number. If I take the example of access point with just a dozen of customers, you reach easily 500,000 access point. And I give you one example. I was looking at how many data points we collect on a network with 11,000 access points, which is a fairly decent network already. But and we looked at when we sum up all of this data, looking at the counters, the RF domain, and all those things, it was about 150 million data points an hour that we were collecting. And the volume of data is extremely small because we compress pretty much everything. But for machine learning, it's gold mine because you're exposed to so much data. And then we do that across customers, as you said, exactly.
So it's not only going to be distributed amongst, it's going to be distributed within an organization, but also within all devices. And it's the learning, the actual AI and machine learning, the cognitive analysis is going to be distributed. So as it's learned, it's then distributed out. And
so, it depends on the use case. So in the first case, which was about the security use case, detecting zero-day attack, you're absolutely right. Everything is actually local, and there was nothing in the cloud. In this other example, this is the opposite. Then in this case, we gather the data, and then we push it, we anonymize, and we learn something in the cloud.
Okay.
Okay, so let me show you another one real quick, which is about predictive analytics, forecasting, as we said. And that's what I was saying before. Observing all of these control points, then we can start building a model. And one thing that is interesting about this one is that we want to have an algorithm that gives you a confidence level. And that's not always the case. Sometimes you forecast an issue, but you have no idea about the probability. And so in this case, it's a little bit like the weather forecast, although it's probably not a good example because they may be wrong sometime. Not in Vegas, right? It's pretty much always sunny and warm. But here in this case, that's what the algorithm is going to tell you. I've got confidence of 4 out of 5. And to be honest, you just have to wait and you see if it was right or wrong. Okay. Do you have any comments about that or any feedback on whether you think this is going to be a promising technology for the future? Any feedback so far?
Well, it seems to be the only way to predict, like you were saying earlier, all the data points. I mean, you can't look at, no one can look at that, not even close.
Well, I think where it becomes super valuable, right? If like you talk about roaming issues, right? Take a healthcare customer. There's a lot of them already moving towards like smartphone-based communications, right? Now you should be able to learn from Apple releases something new. Now all of a sudden we see, you know, whatever iOS, whatever comes out. Now we're seeing a anomaly where a bunch of roaming errors come out, right? You can make a decision now as a business to say, we're going to wait, stay on what we've got until that comes down, and then tackle the upgrade, right?
Exactly. And you know, I worked with a customer yesterday who was telling me that they had 250,000 devices connected in the network, IoT devices as well. You know, and when you have so many types of releases and devices, having the ability to look into an ocean of data. So here, for example, I showed you one axis, which is the type of client, the release, and all those things, and then the access point. We can have a look at it in a different way. We can look at you know, the time, for example. I can give you another one, which was pretty interesting. We found out that it was an AP that used to perform really well. So the machine now compared the AP, the performance of the AP, you know, between now and what it used to do. It could be between access point, it could be between customers as well. That's another request we had for many customers who said, look, I'm looking at the roaming failure rate. It's about 20%. Is it good or bad? We have no idea. So with that solution, we'll be able to compare the networks together. And so we group them by similarity, and we can provide an idea of where you are compared to the other ones.
So question, and maybe this is coming up, but so we see a lot of focus now on the large, you know, the cloud-based analytics, trends, all that stuff. I think, which I think is the right spot for people to focus first. How far in your mind are we away from these sort of things happening with, you know, sort of edge-level compute analysis and then modifying, let's say, policy-driven architecture, right?
Right. So for example, it's an interesting question because when we talk about the architecture, we have to think a lot about where should we gather the data, where do we want to store the data, where do we want to have the compute. So for me, it's more like a use case driven decision. So in the case of the IoT, there's no choice. You know, when you have 3G link and you look at how much of data you would need to push to the cloud, there's no way you can do that. So it has to be locally on the box. And that's why we started with that for ISA 4K, for example. And so in that case, so there was another rationale for it, by the way, which is privacy. And as you know, in some countries, this is pretty strict. And so the fact that we were processing the data locally on the router was really the right thing to do. Now, you know, when you look at wireless or in general the WAN, it's very, very interesting to do that, you know, in centralized fashion. So I don't think we're far. We can do both, actually, quite frankly, now. So the first solution I was referring to is already available. And in terms of the, maybe I can give you some numbers. Off the top of my head, the memory requirement was between 400 and 500 meg on the router, doing the processing real time, by the way. And we took less than 20% of the CPU on one core CPU on an ASR 4K. So it was very lightweight. So there's no constraint, actually, we can run it there. Now, where it's getting really interesting is that the issue of the downside, obviously, is that if you keep everything local, you can't leverage the knowledge across all the equipments, and that's where the cloud becomes really interesting to do. So I think there's going to be a little bit of both, depending on the use case. You think that makes sense?
Yeah.
Okay.
So there was a question that came in across Twitter, and I'm not quite sure I understand the full nuance of what he's asking, but basically, it looks like he's wondering if we can put seed data into the machine learning. So if we have a custom enterprise application and we want to say, okay, here's 10, 20, 30, 40 samples of what kind of fingerprint this application's normal operation has, can we hand that into the machine learning and say, you know, keep an eye on things that vary off of that?
Right. So that's already what we do to some extent. So again, in the case of security, we look at the traffic that goes, because we're running on-premise, we have access to the traffic. So the case of, we do DPI on the DNS request. we look at the structure of a name, for example, and we compute the entropy on the name and start to see if this is something a bit funny, like a weird string, thing like that. So we do some of that, and we consume, if you will, as we consume the data, the knowledge is being encapsulated in the algorithm itself. So we don't need to keep a ton of data because we don't have enough resources locally. But as we learn, we improve the model, and then you can push the model in a centralized location. That's one way to do it.
So essentially, it's going to pick up the fingerprint itself if
Absolutely.
it's common traffic.
Absolutely.
Okay.
That's exactly what it is. Exactly.
Thank you.
Thank you. So what's coming next? Many things. First of all, that new cloud-based project I was referring to will come up soon. We're working on the actual roadmap as we speak, but it is extremely promising. We have a lot of customers who express some interest and just test it. And to be honest with you, I'm not a big fan of slides and PowerPoint. So when we come up with new technology, I say, well, give me your data and test it and see what you can find out. And it's quite amazing when you start to plug these engines. I wouldn't say that it is always right and it does everything, obviously not. There are cases where the rule-based system is actually much better, as I said, but it is super promising. So a few things that I think are really promising. One is really the end-to-end device communication. We know that when you come in with your iPhone, the iPhone has got a lot of intelligence locally, but it's got limited visibility. What is the best access point to connect to? You can only take into account a few local parameters, like the strength of a signal, things like that. But wouldn't it be really smart if this cloud engine could communicate with the access point and say, oh, I know you're trying to do video. You're not connected to the correct AP. You'd better roam to another AP, especially when you can start doing forecasting and prediction. So that's one thing. IoT is another one because, again, so in that case, there's no intelligence locally because, well, there's some intelligence, obviously, but we cannot afford to run too many protocols. And so relying on the network to provide this knowledge for the IoT is extremely interesting. All right, so the last one, it's really about closed loop control. And that may take some time because it will take time before you really trust the system to say, okay, you can detect some issues, you can build some models, you can suggest some changes, and now you guys will automatically close the loop. So we see that in there will be multiple phases, obviously, where we're going to give insight to the customer, we're going to propose some changes, and then you can close with APKM, with an API, and just start doing the changes. So that's something that will take time, but I believe that that's going to be really a very promising avenue. I know that we're running out of time, but we probably have time for a few more questions, I guess. One more, okay?
I asked a similar question in a previous presentation about closing that loop and trusting the system. Just to be more direct, is that a matter of the customer trusting the system with the decisions, or is that a matter of Cisco getting enough customers to have enough data to pipe into the system to trust the system and enable the feature?
Right. So, yeah, it's a good question. I think that's a little bit of both. We want to give a control to the user so that the user can say, hey, first of all, let me see what you guys can do. So the best example is, I can give two examples. One was in the case of security attack. What you can do is, upon detecting the anomaly, the user may say, what are you suggesting to do? And if we suggest to enable some QoS or start storing the data, and you say, okay, you can do that, you click on it, and you start to see the result. If you want to block the traffic, at some point the user may say, okay, I trust you. I see that for these kind of issues, you are pretty good at detecting it and do the right thing. So you can increase the confidence level to a point when you say, if you see it again next time, just do it. And so we leave it to the user to decide on whether to automate the loop. And it depends on the process in the organization as well. Some organizations, they don't like to close the loop automatically. Others would like to react more quickly. In the case of wireless, there's a lot of things we can do. If we see that we can tune up the power of an access point, to make it a bit better, we can activate some QoS again. We can do call admission control to stop some users. So I think that on our end, I can tell you, we are quite quite confident about the ability of such a system to do closed-loop control, but we think that is going to be a question of adoption for the user to say, okay, we trust the system to do something. And it will be driven by, to your point, by policy as well. So at some point, you can enforce policy and say, okay, I've seen that, I trust you, you can do that, go. Do you think that makes sense?
Yeah.
Okay, cool. All right, so we're going to have to wrap up, but you can reach me out, jpv@cisco.com, online, offline, and we'll have some chat together. Thank you very much.
Excellent.
Thank you.
Thank you.